Okay, good morning, Astronomy 1010. Welcome back to the second part of our 12th lecture, I guess. We're going to just say a couple of words that are wrapping up the terrestrial zone, and then I'm hoping we can move towards the Jovian planets today, which ought to be a good time. So, let's start by talking about the climate histories of the terrestrial planets. And one thing I have not tied in yet that I kind of need to do is to talk about the importance of magnetic fields in a planet's magnetosphere and what role they play in keeping a planet's atmosphere wholesome for life. So we can, put this section of our notes as the climate history and magnetic fields. It would be helpful if you guys could remember a couple of things from our earlier lectures about magnetic fields. Perhaps before I ask you a question, I could start by sharing a slide with you that I think I hope will jog your memory. I don't want to be too ambitious here, but let's take a look at my computer is freezing on me. I don't know what the hell's going on today. I might have too many tabs open. Let's look at a little cartoon picture of a planetary magnetic field, just as a sort of meditation point. Jake or anyone else who's hanging out with me here today, actually, hold on. You know what I got to do? I got to hide the trolls because I can't focus on the people who are sharing their videos with me if you guys are clogging it up. Hide non-video participants. Okay. All right. So there's 3 of you, anyways. Do you guys have any recollection of what the 2 conditions are for a planetary magnetic field? Jake, Andrew, Frank?
You said, was it the rules of magnetic fields?
No, well, those 3 rules were to sort of tell you what a magnetic field was and where it comes from. But then we connected that to the magnetic fields of planets, and we said, based on those rules, this is why a planet would have a magnetic field. Sorry,
one of them is they have to have a hot interior.
Yeah, probably with liquid metal in the core. We believe that the liquid metal becomes partially ionized, and that's what gives you the charges, I believe. So that's good, Jake. A hot interior with a liquid metal core. And what would the second one be?
A rapid
Would it be
rotation.
atmosphere?
Sorry, Frank, Jake's got it again. It's the rapid rotation. Because you need the rotation to circulate the current. Remember when I was telling you about rules for magnetic fields, wherever the bloody heck they were. Oh, I'm sorry. Maybe it was in the lecture on the sun where I showed you rules for magnetic fields. It's all coming back to me now. So I guess I want the sun lecture too. Remember, I told you that a dipole magnetic field is created when charges are circulating around in a circle. That's how you get a dipole magnetic field. So the rapid rotation ensures that whatever charges are inside the Earth are kind of sloshing around inside of a circular pattern. So which of the terrestrial planets have magnetic fields? What are the terrestrial planets?
Mercury.
Mercury.
Mars.
Mars.
Earth.
Earth.
Venus.
Venus. Okay. So which of those 4 planets have magnetic fields?
Does Earth have one?
Earth has one. And that's it. Neither Venus nor Mars nor Mercury. Well, Mercury's got a weak magnetic field, but we ain't going to talk about that. For all intents and purposes, Earth is the only terrestrial planet with a real magnetic field. Magnetic fields protect atmospheres from the solar wind. Let's take that as a note. A magnetic field, and this is an important planetary science concept. I can't tell you how much time I spent in graduate school discussing magnetospheres. A magnetic field creates a magnetosphere. It's not an atmosphere layer, it's a magnetic bubble layer. A magnetic field creates a magnetosphere around a planet that protects the atmosphere from harassment by solar wind ions. So it's magnetosphere versus the solar wind. It might be nice for me to just kind of show you a cartoon from the internet here. Magnetosphere. Usually if you research magnetospheres, sorry, I spelled that wrong. Hopefully not on the board. You'll see some kind of a picture like this. This is an excellent picture, a diagram of a magnetosphere. So Earth has a geomagnetic field, and it creates this kind of magnetic bubble around the Earth, such that when the solar wind ions come raining down on us, they would normally be like little microscopic bullets that are constantly smashing into oxygen and nitrogen molecules in our exosphere. But instead, they get trapped by the magnetic field, and I'm going to kind of draw their path here. They get kind of sloughed off because the particles gyrate around the magnetic field, and they get pushed off into outer space, almost like hair blowing in the wind or something like that. Almost like your hair protecting your scalp from rain droplets or something. Can you guys remind me a little bit about the solar wind? I'm assuming that you remember what the solar wind is, but I'd like to be 100% sure of that before I continue. Hello, Andrew. Andrew, you're always in a new location. It's always a surprise to see your background. It looks like you're tending bar or something. Okay. All right. Can you guys remind me about the solar wind? Tell me something interesting. Tell me about solar wind ions. What do you know? Remember this thing? Wait, here we go. What do you know about the solar wind? I showed you this video before. So was I right when I assumed that you've all forgotten what the solar wind is?
Is it like a big wave of ions?
Yeah, okay. A stream of ions. What kind of ions, Jake? Jake, do you know what the composition of the sun is?
Not off the top of my head.
Okay, well, at least you're talking to me. I'll take that. Does anyone know what the composition of the sun is?
Hydrogen,
Hydrogen and?
helium,
Okay, so Joel, if you ionize a hydrogen atom, what would you get?
helium.
No. Helium is,
No,
what does a hydrogen atom look like? What's it made of?
proton,
And?
electron.
So if you ionize them, what particles do you have?
H2.
No. H2 is molecular hydrogen. I'm talking about one hydrogen. Look, guys, I'm asking you a simple question. I'm starting to worry that your basic science skills are going out the window here. Look, here's a proton, here's an electron. They are bound. If I separate them, what do I have? I have two particles.
One electron, one
Proton.
proton.
Effing Christ, yes. Okay, guys, you're scaring the bejesus out of me. Hey, we could get out crayons and just color if you want. I don't know. I don't want to push you past the breaking point here, okay? Look.
I'll fail even worse.
Okay, look, I'm getting a little scared here. I did have an idea about the final exam. Okay, listen, I'm gonna pause this recording for a second.
We'll just do a poll.
Okay, so we're gonna get back into our lecture here. We can talk about the exam structure next week. So if you ionize the components of the sun, which is hydrogen and helium, you end up with protons, you end up with free electrons, and if you ionize a helium nucleus, who knows what a helium nucleus is?
Is that deuterium?
No, deuterium's hydrogen. I'm talking about helium. It's a different element.
Oh,
What's a helium nucleus?
crap. Oh, just nucleus.
I don't expect you to know how many protons are in a uranium or a molybdenum atom, but I was thinking you might know how many protons and neutrons are in helium. The
That
second
two?
Two protons, two neutrons. Helium nuclei, also known in physics as an alpha particle. These are the solar wind ions. Mostly it's protons and electrons, with 1/10 or so being helium nuclei. That's the solar wind. And when those solar wind ions strike your atmospheric gases, bad things can happen. For instance, let's say you're a diatomic nitrogen molecule. Diatomic means there's two nitrogens floating around. You're huffing this stuff every moment here, you're breathing. And along comes some high-speed proton from the solar wind, bam, and it smashes into this thing. It can break this apart, and it can kick one of those nitrogens at some high velocity into space. That sort of reminds me of our thermal escape discussion, where you could hit an atom so violently that it picks up kinetic energy and just goes whoop, flying away into space. Especially because the atmospheric gas they're going to hit is in the exosphere, which is the layer that bleeds away into space. Magnetospheres protect planets from the harassment due to the solar wind. Here you can see a large eruption called a coronal mass ejection. And a moment after the eruption, you can see the static on the camera as those high-speed protons and electrons strike the CCD camera and create electrical disturbance. I cannot show you individual protons and electrons because they are too microscopic to see, but you can see them in the electronic interference they cause with the camera there. You can also, of course, see them in the aurora borealis. The aurora is kind of like what happens after the ions slow down a bit. From the magnetic field kind of slows them down, and then it just tickles the atmosphere to make a light show. I think we should try to draw a picture of how a magnetosphere works. I found that helpful to understand it. Okay, so let's draw a little cartoon here. We'll have Earth. Okay. And we'll draw its magnetosphere with green for magnetic fields. So normally it's a dipole magnetic field, but what the solar wind does is the other part of the dipole kind of gets morphed by the solar wind into these long magnetic tails that stream out from Earth, okay? So basically what we do is we have, we'll use red for the solar wind. So here comes some solar wind ions. Now there are electrons in here too, but I'm just drawing the protons for simplicity. And they're striking the magnetic fields. Most of them get sloughed off to the other side. Some of them will kind of wiggle their way down towards the North and South Pole. but they'll lose a bit of energy. Their kinetic energies will be reduced, and they'll create the aurora borealis on Earth. Now, you might wonder why I'm telling you about this. Excuse me. I'm telling you about this because this plays a role in the dynamic evolution of a planet's atmosphere. Let's take a think about how things were different on Venus, or let's say, yeah, Venus versus Earth, if we look back at their climate histories, okay? I'd like to show you guys, by the way, this was one picture of magnetosphere that I was trying to have you draw something like this, okay? This is another diagram of how it works. People make all kinds of interesting models. Here's another diagram. So I spent a lot of time in graduate school looking at pictures like this. Here's the solar wind. Oh, sorry, that's not a very high resolution one. So this is a kind of more professional illustration of how a magnetosphere looks. It's kind of like a protective magnetic bubble around your planet. It's very cool. Okay, so I want to show you guys a couple of different cartoons here. Bear with me. Yeah, I think this is it. No. I want the atmospheres lecture. There we go. Okay, so let's just talk about two competing and different views of how a planet might evolve over time. Last time we learned a little bit about the CO2 cycle. Before I go forward here, can you guys explain the CO2 cycle in a nutshell to me? Feel free to use your notes if your memory is no good. What happens in the CO2 cycle on Earth, and why is that important for climate stability?
CO2 gets released into the atmosphere through volcanism, and then
Good.
it gets like absorbed in like the clouds and the rain, and then it
Yes.
rains, and then
Yes.
washes over rocks, I think, and like gets
Silts.
swept back into the ocean, and then becomes like coral reefs and like.
And the important part of those reefs is that you're trapping the CO2 on the seafloor bed, right, Jake?
Yes,
Jake,
in the
you are
form of
doing
coral reefs
excellent.
and special rock, which I forget the name of.
They call it carbonate rock or limestone,
Carbonate
something
rock.
like that. Yeah.
And then plate tectonics shifts the seafloor, and then it ends up going back into the subduction zone, and the whole process starts over.
Exactly. That was beautifully done, sir. Thank you very much. Okay. So by the way, if you are going to take a test, those are obviously going to be questions on there, and you sound ready to answer them if necessary. This works for a couple of reasons. Earth is at the right temperature for a lot of the water to condense into oceans. So you're ready for the rain to come down and to take that CO2 across the silicate rock and down into the ocean floor bed. Imagine how things would be different if the solar wind had been messing with our atmosphere like it did on Venus. Here's an alternative picture. Venus started out just a little bit too hot, meaning most of its water was not going to condense onto the surface of Venus, but was going to remain in the form of steam in cloud layers. Add to that the fact that Venus does not rotate, and despite having a big hot interior, without rotation, Venus doesn't have a magnetic field. Now, at first you think, who gives a crap about the magnetic field? And then you realize, whoa, hold on a second. What's going to happen to those water molecules when they get continuously bashed by solar wind ions? The solar wind is going to come beating down on the cloud tops of Venus, and they're going to strike into those water molecules. And let's remember what a water molecule looks like. It's one oxygen, right? And then I'll use blue for two hydrogens. Sorry, I'm not good at drawing with my mouse, but I'm trying. So here are your two hydrogen atoms, right? Well, hydrogen is water molecules are heavy, so Venus's gravity can hold on to them. But if the solar wind hits a water molecule, well, bam, it's going to break those hydrogens off from the water molecule. And hydrogens are light. So what are the hydrogen atoms going to do? They're going to thermal escape because their velocities or their kinetic energies are high. This will leave behind these sort of deadly OH ions. OH ions, I think they call it hydroxyl or something. Someone in chemistry might be able to help me with that. These OH ions are highly reactive. Ever heard of, what do they call these things? Free radicals. These are like free radicals, all right? Ever hear about that? You got to drink tea so you can kill your free radicals. Free radicals are things with charge that want to violently react. Well, those OH ions interact with sulfur dioxide and they form this highly toxic acid rain clouds, kind of like in the movie Aliens that dissolves like the metal in the spaceships, right? So Venus has acid rain because of these water molecules that were broken apart. Now Venus is doubly, triply screwed. It's already hot. Now you've got no water to trap your CO2. You've got a bunch of CO2 forming a big greenhouse layer, and you add some acid rain. Moral of the story, Venus is a crappy place to take a vacation. And by the way, a similar story happened on Mars as well, although I didn't have the same cartoon picture. I wish I had gotten a third sequence here. So maybe we can just take a quick note on it to help you remember if necessary. The difference between the climate histories on Earth, Venus, and Mars is kind of like the tale of Goldilocks and the three atmospheres, okay? And the temperatures too. So if you think about Earth, Earth has a sort of a temperature for liquid H2O, and H2O and CO2 start the so-called carbon cycle and trap CO2 on the ocean floor. Also, Earth has a magnetosphere, and the magnetosphere is going to protect the water molecules in our atmosphere so that they can capture and dissolve CO2. We saw something different on Venus. Venus is a little bit too hot, so we have water in the vapor form. We have solar wind ions break apart water molecules. That means no CO2 is trapped. That's the big thing. So your planet starts to overheat. And OH plus sulfur dioxide form acid rain clouds. Oh, we should mention the solar wind ions can do this. Why? Because the slow rotation didn't create a magnetic field. In some ways, all of Venus's troubles, well, Venus's troubles are a two-part martini. It's no magnetic field, and it's too hot. Those are the reasons why Venus didn't evolve as lovely as Earth did. Let's try to do one more. Let's try to do Mars here. Actually, before I tell you, do you think you guys can predict what happened on Mars? Does Mars have a magnetic field?
Well, it has a slight atmosphere, so
Right, but what are the two conditions for a magnetic field?
A hot inner core.
Does Mars have a hot inner core, Jake?
No.
Its lithosphere is very thick today. It probably did in the past. So Mars cooled rapidly. The cooled interior probably caused Mars to lose its magnetic field. This in time allowed the atmosphere to thin. I'm going to say the atmosphere thins. I don't think that's a word, but whatever. The atmosphere thins out, and then water evaporates into vapor. Now what's going to happen? Once water is in Mars's upper atmosphere, what's going to happen to it?
It's going to float away.
Water molecules are too heavy to float away. There's another step in the process.
It'll fall to the surface and just freeze.
No. No.
The solar wind will start hitting it and separating the hydrogen and the oxygen atoms.
Excellent, Andrew Bates. Excellent. So the solar wind, it's going to break H2O into oxygen and free hydrogen. What's going to happen next, Andrew, since you're doing so damn good?
The hydrogen's gonna float off into space.
Good. The hydrogens are light, so they'll escape. So the hydrogen escapes due to thermal escape. What's going to happen to the oxygen? The oxygen's too heavy to escape, Andrew.
Well, you explained that it's gonna mix with the, it's gonna eventually lead into acid rain clouds.
No, that was on Venus. By the way, I don't know if it's going to have O2. We'll just write oxygen. Get rid of the little 2.
I'm not sure then.
There's no acid rain on Mars. What does the oxygen do? The oxygen is too heavy to escape. Oxygen chemically reacts with the surface of the planet, and it rusts the surface, turning the surface of Mars red. So basically, when you see this picture of Mars, where are we here? Sorry. The entire surface of the planet has become red because oxygen has chemically reacted with the surface. Screw this. Let's get a. I was dumb when I made these slideshows. Mars planet. Look at this right here. The entire damn surface of the planet today is covered in red terrain because basically the oxygen that was once part of that free-flowing water on Mars has rusted the surface red. Everywhere you go, the whole planet is the same color, except for maybe the ice caps. Pretty cool, right? You can see Mars's lost water in the red surface of the planet. What's the moral of my story, if I have one at all?
Oh, I can't see the bottom.
Can you now?
Yeah, I got it.
What is the moral of my story?
Magnetic fields are needed for life. almost?
Kind of, yeah. Wow, Jake, I didn't expect you guys to get that. That's right.
Yeah, I'm pretty smart.
You are pretty good, actually. Jake, that was exactly what the hell I wanted you to say. That in a messed up way of thinking, magnetic fields are necessary to create a stable environment for life, isn't it? So I guess, Jake, if you were going to design an interstellar mission, if you discovered like 27 or maybe even 2,700 habitable, or let's say you found 1,000 habitable worlds, the ones that you would be most willing to send a spacecraft to would be ones that had a magnetic field. Isn't that true?
So then the question begs to be asked, why the hell are we trying to civilize Mars?
It's relatively pointless. I mean, well,
Okay.
you could live, well, I don't know. Look, people live in all kinds of hostile environments. You know, what people go to Antarctica at the McMurdo station, and they spend a year down there doing science experiments. So there are plenty of people who'd be willing to live in a bubble on Mars for the pleasure of studying Martian geology and stuff. It is never going to be Earth 2.0. You're not going to be able to terraform Mars because it suffers from some planetary-wide problems that have doomed it in the first place. Its mass is too small to generate a lot of internal heat, so it lost its magnetic field. And even if you started pumping atmospheric gases, like in some kind of science fiction movie, like in Total Recall, where they put the alien hand in and Arnold flies out into the surface. Remember that at the end of Total Recall? Kind of like that movie. All right, anyway, so those atmospheric gases would be subject to the same solar wind harassment that it was in the first place. So over time, you'd be fighting a losing battle. It'd be kind of like turning the heat on and opening up your windows. You know, it would be, you could do it, but it's a defeatist kind of thing. You know, one of the cool things about Jovians, if I can make a kind of segue here, the other planets that have magnetic fields are all Jovian planets. So there's kind of this wacky relation. The one thing that Earth has in common with Jovian planets, and there's not much that it does have in common with Jovian planets. And I'm certainly not meaning to imply that Jovians are good for life, because they don't really have solid surfaces or anything. But Jovian planets, being big, warm, and rapidly rotating, all have magnetic fields. So there's this one kind of brotherhood or sisterhood that we share with the Jovians, in that Earth is the only terrestrial planet to have a magnetic field. Magnetic fields of the provinces are big, fastly rotating planets. Had Venus rotated faster, its magnetic field probably would have protected its atmosphere a bit. And it might not be Earth 2.0, but it definitely wouldn't be the nasty hellhole it is today. That's going to be in your homework, by the way. Okay, I'm going to erase this. Andrew, does everyone have these notes? Because I need to move on.
I'm all set.
Okay, thank you. I'm glad you could have that talk, because that kind of sums up everything we've learned in the last 2 weeks and kind of puts it together into a real story, which I think is nice. Okay, why don't we transition into the Jovian planets, or the gas giants? This is chapter 11, Jovian Worlds, also sometimes called the gas giants. What are we dealing with here? Well, we've got Jupiter, the king of the Jovians, right? We've got Saturn, we've got the planet Uranus, which is green, kind of like a green featureless ball. Actually, it's sort of tilted on its side. Should have made it a little smaller. And then we have Neptune. Neptune is blue. In later years, it's become customary to refer to Jupiter and Saturn themselves as gas giants, and to refer to Uranus and Neptune as the so-called ice giants, because they have slightly higher concentrations of icy methanes and things. I'd like you guys to remember that when we cross from the terrestrial zone into the Jovian zone, we traverse across this imaginary boundary in our solar system called the frost line. And the frost line is a transition from terrestrial to Jovian planets. We also cross this other boundary, which is the asteroid belt, right? The asteroid belt, shown here, runs from about 2 astronomical units to 3 astronomical units. And the asteroids are clumps of rocky debris that lie between the orbits of Mars and Jupiter. And the asteroid belt is kind of like a transition from the terrestrial world into the Jovian world. Okay. So the composition of all Jovians is roughly the same. Let's write it down. It's kind of similar to that of the sun. It's 70% hydrogen. Maybe 28% helium by mass. Now, in the sun, the remaining 2% were metals because the sun is so hot that everything is in the atomic gas state. But in a colder environment, roughly 1% are in the forms of things that I'm going to call ices. And the remaining 1% is in the form of stuff that's pretty much just rock and metal. And this is the recipe to make a Jovian planet. It's basically a raw, uncut mixture of the pancake batter that made up the so-called Proto-Solar Nebula. So probably, let's see if I can get a slide here. We'll talk about the moons a little later. If you could imagine that proto-solar nebula, the Jovians would have condensed directly out of that material. Here's a artist illustration of what it might have been like if you could have watched Jupiter forming from that disk that made up the early solar system. It's basically an untouched composition of all the materials that were in the proto-solar disk. Now, planets like Earth and Venus did not keep all of that hydrogen and helium. Do you guys know why? Why didn't Earth end up with significant amounts of hydrogen and helium?
Is it because all of that went to the sun?
No. Nope. That had too much rotation. Not at first, no. There's a much simpler explanation.
Because they're too light.
What's too light?
The particles.
Which particles? I'm not saying you're wrong. I just need you to flesh out the answer because it's a little vague.
I purposely gave it vague because I'm just stabbing at it.
Well, you're hitting pretty close to the
So
target.
the electrons.
No.
Oh.
Hydrogen and helium are light gases. Earth does not have enough mass to capture hydrogen and helium. If you did a thermal escape problem with hydrogen, you'd find that hydrogen can leak off into outer space. Maybe at first when Earth formed, there was a little bit of hydrogen and helium around it as a temporary atmosphere, but it would have boiled away in a very short time period. You literally need these massive objects in order to capture those light gases. Probably they started out as a chunk of ice and rock. We'll talk about that in a minute. Actually, guys, I want to take I'm taking a lot of pauses here today, but if you can just bear with me for a second. Sorry about that. We've talked about the composition of the gas giants, and I want to elaborate a little bit about ices, okay? These are things called hydrogen ices, and they have similar properties to that of water ice. We sometimes call them volatiles because they have very low sublimation and evaporation points. And I'm going to explain what I mean by that. I'm going to erase this beautiful picture here. Let's do a little tidbit on hydrogen ices. Or volatiles. Of course, there's water, which, as you know, is H2O. And the arrangement is that you have a big fat oxygen connected to some tiny little hydrogens. So one oxygen and two hydrogens, right? Then we have ammonia, whose chemical composition is NH3. That's one nitrogen atom connected to three little hydrogens in a sort of tetrahedron shape. They call the shape of this molecule tetrahedronal because it makes a little tetrahedron. And then there's methane. Methane is CH4, and that's a carbon atom connected to four little hydrogens. I think you guys can understand why we call them hydrogen ices. They're atoms like carbon, nitrogen, and oxygen that are attached to hydrogens. And they have somewhat similar, well, they behave differently. Obviously, you can drink a glass of water. You don't want to drink a glass of diluted ammonia. But they behave similarly in terms of their volatility. The fact that they're ice at very low temperatures, but if you heat them up a little bit, they quickly sublimate into a gas. Under pressure, they can be liquids. By the way, kind of a nice tie-in with my astronomy 1020 class. Joel, who's taken my 1020 class, and I think Frank and Andrew Bates too, right? You guys might remember from 1020 that carbon, nitrogen, and oxygen are some of the most abundant atoms in the universe after hydrogen and helium. So we would expect that these would be common molecules in other star systems as well, which is kind of interesting. Even though it's not technically a hydrogen ice because there's no hydrogen in it, I would like to make an honorable mention to CO2. So think of this as your honorable mention category. Carbon dioxide is also similar in that it becomes an ice at low temperatures and then quickly turns into a vapor or a gas. So carbon dioxide could also be kind of considered. By the way, there's colors associated with each of these things. Of course, water and CO2 create white clouds. I don't have the proper color here, but ammonia famously makes yellow clouds. Was Frank or Andrew, did one of you do the spectroscopy lab with me and had color blindness? I think it was one of you guys, right?
Yeah, that was me.
Does that look yellow to you? Looks orange to me, but.
Yeah, it looks orange.
Okay, yeah. All right. It was the closest I had to yellow, so. Methane famously creates blue clouds. Oh, I would like to make one more honorable mention. Normally, this gas would be a little bit more esoteric, but it turns out to make up some of the cloud tops of Jupiter. It's called ammonium hydrosulfide, and it famously makes red clouds. So I'm going to put those down in the honorable mention category. Okay, ammonium hydrosulfide is also the thing they use to make stink bombs, if you guys have ever heard of those. The chemical composition, I'm not a chemist, so you're going to have to work with me here. Ammonium hydrosulfide. I know it's like NHSH4 or something like that. I'd like to not screw this up for you guys. NH4HS is how they write it. NH4SH. Okay, let's do that. I'm not going to draw this one out. This is called ammonium hydrosulfide. And one of the reasons I would like to mention it is because it is responsible for the red colored clouds on Jupiter. CO2 also makes white clouds, by the way. I'll just give a second for you guys to get that. Okay.
Yeah, I can't see. Oh,
Oh, sorry. Andrew, let me know when you're done.
all right, I'm all set.
All right. So I want to show a picture of Jupiter to you guys. Oops. Let's keep this handy. And let's go to our Jovians. There we go. And let's look at a high-res image of Jupiter from the Galileo mission. Can you guys see can you guys see those different colors that we were just describing there? You can see the ammonium hydrosulfide in red. You can see the yellow clouds of ammonia. The white clouds are water. And you can even see little flecks of blue in there, can't you? From perhaps little bits of condensed methane or something. So you can see almost all of the different colors present in the atmosphere of Jupiter. Did you guys ever think it's weird that all the Jovians formed far from the sun and all of the terrestrials formed close to the sun? Doesn't that seem just a little bit not random, a little bit coinky-dinky, you know? Let's look at the solar system together. And let's do a cartoon. I need to share the screen with you guys. Why would it be that these terrestrials form close to the sun, but all the Jovians formed far from the sun? Can you guys think of a good reason for that? It's got something to do with the way planets form and how they capture material from the proto-solar nebula. So let's talk a little bit about the formation of the solar system. And in a way, what I'm trying to do is I'm trying to talk to you guys about the realm of the Jovian planets and why Jovian planets should be located far from the sun. If you could go back 4.6 billion years ago to when the solar system formed, you would see this swirling disk of hydrogen and helium gas with bits of rocky and icy debris in it. Some of the material would be rotating too rapidly around the star, and it would have too much angular momentum to fall into the sun. In the same way, Earth's orbit doesn't crash into the sun because it's got too much spin going on. Over time, some of that material would begin to condense. First into static cling, the tiniest grains and bits of rock and metal would begin to clump together through collisions and static cling. And once they formed an asteroid-sized nugget, they might pick up enough gravity to start pulling some material from the proto-solar nebula. The Jovian planets formed with a pretty consistent composition to the proto-solar nebula, which is hydrogen and helium and a bit of grit. But the terrestrial planets didn't form with any hydrogen or any helium, probably because they weren't massive enough to capture them. The real question is, why did the little seedlings of, sorry, I'm coughing a lot today. Little seedlings of planets are what are known to astronomers as planetesimals. Maybe I can try to find a picture of a hypothetical planetesimal. A planetesimal would be the sort of little tiny bits of debris and rock that would stick together to make up the initial formation of the planets. So if you watch the time lapse of how a planet formed, they would start with these little clumps, even tiny grains of sand, and through collisions and static cling would begin to stick together into something a little more massive. And the more massive things would probably resemble kind of like asteroids or something, right? Something like this. We call them planetesimals. And then collisions and gravity would bring them closer together. You want to know what I think a reasonable approximation to a planetesimal would be? An asteroid. Except the planetesimals would not be the same depending on how far away from the sun they formed. Remember that in the early solar system, the protostar that is forming as the sun is going to be extremely hot and giving off lots of radiation into space. And that means the closer you get to the protostar, the closer you get to the sun, the warmer and warmer temperatures will be just due to solar radiation. When you are close to the sun, rocks and metals can stay in the form of solid grains, but these hydrogen ices and volatiles will sublimate from the ice phase into a gas phase. And as a gas, they cannot accumulate into those asteroid-like planetesimals. However, once you cross a certain threshold, a threshold known as the frost line, the temperatures will drop sufficiently where now the bits of ice can also form solid grains that will contribute to your planetesimals. Do you guys get what I'm talking about here? Why would the presence of ice eventually lead to the formation of massive Jovian planets? We might want to write this down because this is a lot to think about. The concept I'm trying to bring up with you guys here today is the concept of the frost line. And I'll do more Jovians next time, but this is something useful for us to do. The frost line is the distance from the early sun, probably in the form of a protostar, at which hydrogen ices transition from gas or vapor into solid ice grains. These solid ice grains add mass to the early planetesimals. Here's another fancy word. Planetesimals are like baby protoplanets. They're the seeds from which planets form from. A planetesimal is basically a planetary seed. And we'll write that in parentheses. The solid ice grains add mass to early planetesimals, allowing massive Jovians to form, which basically can capture the hydrogen and helium gas that is abundant in the early solar system. Hopefully that makes some kind of sense to you guys. Do you know what I think we could do before our class ends? I bet we could compute the frost line. Can you guys think of a formula that I might use to compute the distance of the frost line? A formula that we're going to use in our homeworks today? A formula from like a class ago, maybe 2 classes ago. We'd have to know like the temperature at any distance from the sun, right?
The ideal gas law?
Say that?
The ideal gas law?
The ideal gas law gives you temperature based on density and pressure. It might be difficult for us to estimate the pressure in the protosolar nebula because it would vary. I was thinking of a simpler formula that involves temperature. Temperature as a function of distance from the sun. I'm falling apart today.
You said the B formula. I forget the name of it. Does it begin with the B?
The inverse square law is part of it, but we actually used it to create a new formula.
The no greenhouse formula?
That's right. That's right. Can I erase this? Andrew Larson, where are you at?
I'm at the end.
All right, just let me know when you're done. We got this?
Yeah, I got it.
This will be our last bit for the day. Let's find the frost line. What is the temperature of, what is the freezing point of water?
32 degrees Fahrenheit, 0 degrees Celsius.
How many Kelvin is that?
$273.
Nice. But I've got some bad news for you guys. This is the freezing point of water at 1 atmosphere of pressure. That is not the freezing point of water in space, because without an atmosphere, it's much easier for those particles to sublimate. Please remember this statement. There are no liquids in space. Do you understand? There is no liquid in space. In space, you are solid or you are gas. Liquid is something weird that happens under atmospheric pressure. In space, the freezing, or you might even say the sublimation point of, let's take ice, is a temperature of 160 Kelvin. And help me compute that, guys. If you do,
That'd be minus 113 Celsius.
is that right?
Yeah, because you subtract 273 from it.
Yes, thank you. I'm not sure what that would be in Fahrenheit, but pretty effing cold, right? That might be like almost negative 200 Fahrenheit. You know what? For James Quinn, our night student who is still using Fahrenheit in his vacuum chamber, let's do a Google thing. So 160 Kelvin to Fahrenheit. Negative 172 Fahrenheit. Wow. Cool. So let's apply the no greenhouse formula. 280 Kelvin times the 4th root of 1 minus the albedo over the distance squared. Here we're doing something kind of perverse. Our goal is to plug in 160 Kelvin here but instead to solve for the distance of the frost line. If we plug in 160 Kelvin there, we'll get this frost line for the distance, but we're going to need a global albedo. And here, usually I pick on Noah for albedos, but I'll have to pick on someone else today. Let me show you that picture of different albedos. Come on, Brendan. That's the planetary geology slideshow. Where's the atmospheres? Okay, I'm struggling here. Oh, there's planetary atmosphere, sorry. Okay. Here's a picture of some albedos. What would you guys say is a typical albedo for ice in space? What albedo shall we choose?
7%.
Why 7%?
It's the moon.
The moon is made of rock. We're talking about ice.
80 to 95.
Who said that?
Mateus.
Oh, I didn't realize you were hiding back there, Mateus.
I'm a troll today.
You're trolled today, huh? Jeez, guys. Okay, Mateus, weirdly enough, Joel is more right than you are. Mateus, I can't blame you. I would have said 80 to 95%, thinking that ice was shiny ice. But let me show you some pictures that might open your eyes a bit. There was a famous spacecraft called the Rosetta spacecraft, which traveled for the first time to see a comet nucleus called 67P Gerasimchenko. And they had some beautiful photos in the New York Times, and I captured them for you guys. All right, now I'm notoriously terrible at planet. All right, there we go. Well, Rosetta Comet landing at File Organization. There we go. So the Rosetta spacecraft was pretty darn dope. The Rosetta spacecraft was one of our first missions to go flying past a comet and to attempt to drop a washing machine-sized probe onto a comet's surface. Now, why comets are interesting to planetary scientists is because comets are basically like 96% ice and maybe 3% bits of rock and dust and dirt. For that reason, they represent a pretty pure sample of the Proto-Solar Nebula, and scientists wanted to test the composition of the water on comets to see if it had the same concentrations of deuterium as water in our oceans. And that's because there's sort of two competing theories about how oceans might have developed so large on Earth. One is that volcanoes just kept outgassing and outgassing and outgassing, and then eventually they condensed into the oceans. And the other idea is maybe a whole bunch of comets pegged the Earth and deposited water there. To do this, they dropped a washing machine-sized probe called Philae on the surface. Here's a little picture of the probe after it was launched, and it's descending onto the comet. Now, comets, being small, have so little gravity that they had to design these ice harpoons to jam into the ice and lodge the spacecraft into it. That's because you could literally jump off of a comet nucleus and achieve escape velocity. So they were worried that if the washing machine just like hit the comet's surface, it would bounce off of it and fly away into space. So they designed these two ice harpoons to clamp into the ice and pull it close so we could drill it and take a sample. Well, best laid plans of mice and men, when they deployed the washing machine probe, it hit the comet and one of the harpoons or something failed and didn't grab the ice. And so the washing machine went bouncing around the surface of the comet and landed kind of upside down in the shadow of an ice boulder. So they could take pictures from the thing and they could see out onto the comet, but they couldn't figure out which boulder it had gone into because it was so chaotic. I'm going to show you pictures from the descent of, or the approach of the spacecraft. So here's a whole bunch of pictures. And remember, this object here is 96% ice. Here we are getting closer. What color is the surface of this icy comet?
Looks black, right?
Jet black, Joel. This is ice, but it ain't no clean, fresh as the driven snow ice. This is dirty ice. This is like the ice that's under your tires in the city in the winter. This crap has been kicking around the solar system for 5 billion years, while dust grains and little bits of cosmic poo stick to its surface. It is the dirtiest ice out there. And look how freaking wild this stuff looks. Look how it looks like pancake batter with pebbles in it or something. It's so cool looking. You can actually see jets of sublimating gas shooting off the surface. Can you see that? This comet, this is the only comet nucleus we've ever had a glimpse of. And by the way, I was teaching when this happened. This is roughly the size of the comet in comparison to like New York City. It's smaller than New York City, okay? That was the first time I'd ever seen the nucleus of a comet. So it was pretty jaw-dropping to me. The point here is that the average albedo of a comet is usually like 5% or less. So paradoxically, whereas Mateus would have said, oh, I think it's 97% or something really shiny and reflective, it turns out a better albedo would be like 5%. Okay, we're going to plug in those things, we're going to solve, and then we'll take a break. But I'm building up towards a point here, if you guys can work with me. Okay, so I have some math here. 160 Kelvin equals 280 Kelvin times the fourth root of 1 minus 0.05 over the distance squared. And I want to solve for the distance squared, and that's not too difficult to do. First, I divide both sides of the equation by 280. The kelvins cancel, and I get 160 over 280 equals the fourth root of all that stuff. And then what I'm going to do is I'm going to take the fourth power to both sides. And when I take the fourth power to both sides, I get 160 over 280 to the power of 4 is going to equal, let's see, 1 minus 5% should be 95% divided by the distance squared. I'm going to flip the d squared up and that doodad down. So this becomes d squared equals 0.95 over 160 over 280 to the fourth power. And now I'm going to take the square root to solve for the distance. And then we're going to compute it. The square root of 95% over 160 over 280 to the fourth power. I'm worried y'all are going to run into order of operations issues, so let's do this together, okay? So we'll do, I'm trying to show you my calculator and the formula at the same time. Okay, so let's do 95%. And let's divide by, open parentheses, 160, divide by 280, close parentheses, to the power of 4 equals. And that's everything that's inside the fourth root. Sorry, the square root. And then we take the square root, shift, square root. And my answer is approximately 3 AU. Class, why do I find that answer interesting?
Because that's just outside the asteroid belt.
Exactly, Joel. Basically, the frost line is right at the edge of the asteroid belt where the Jovians begin. That's the edge of the asteroid belt. And the whole point of this is to try to help you. This was a mind-blowing exercise for me because it made so many things clear about the solar system to me. Why the Jovians should have formed at the outer parts of the solar system and the terrestrial planets should have formed at the inner side of the solar system is because once you cross that boundary, right, here you only have rock and metal making up your planets. But out here you have rock plus metal and ice. And because there's so much more ice, the seedlings of your Jovians could swell to tremendous masses. And to drive that point home, in fact, a comet is kind of like a failed Jovian seedling. To drive that point home, if this function of 5, if this was a planetesimal that would have created a terrestrial planet, this is probably what a Jovian planetesimal would have looked like. It would have been a dirty snow. It would have been a snowball with a rock in it. That's pretty much what it would have been, right? Okay, so we ended on an interesting point. Sorry about all the interruptions today. Why don't we take a little 15-minute break? Do you guys want the 15-minute break? Yes, you do, right? Okay, and then we'll crank out the homework for chapter 10. I'll see you guys in a bit. Okay, shall we get to it?
Which homework are we doing?
Number 10.
Homework 10.
Do you guys have those questions? Let's do the things that we always do.
Yeah, I got him.
Name. AS1010. Whatever your section is. Chapter 10. All right, Jake, let it rip.
52, 57, 61, 62, and 65.
Okay, Jake, why don't you read us chapter 10, number 52, and we'll get right to this.
Sure. Swiftly rotating Venus. Suppose Venus rotated as rapidly as Earth. Briefly explain how and why you would expect it to be different in terms of each of the following: geological processes, atmospheric circulation, magnetic field, and climate history.
Okay, let me go over those again. So geological processes, right?
Yep. Atmospheric circulation,
Okay.
magnetic field, and then climate history.
This is actually a lot of ground to cover. So before we start this epic answer, let's just make sure that you guys have the gist of it, because this is directly related to what we talked about in our class today. So what's up with the magnetic field if Venus rotated? More rapidly. Today, Venus has a very slow to minimal rotation, right? How would a rapid rotation change Venus's magnetic field?
It would be stronger.
How would it change atmospheric circulation?
Would it create more of those Hadley cells?
Excellent. We're going to talk about that too. How would that affect geology? The combination of magnetic field plus atmospheric circulation. What type of geology does Venus have on its surface today?
Isn't it
What-
just like rock?
Well, right, but rock isn't a
Okay.
geological. What of our 4 geological processes are active on Venus?
Erosion.
Fuck no.
Volcanism.
Volcanism is the only one. Let me, sorry, I shouldn't have said that. Listen, the reason why it's not erosion is although Venus has a thick atmosphere, it baked all of its water out, all of its ice out. There's no ice, there's no water. And because Venus does not rotate, there's no wind. Venus has a stagnant atmosphere. So there's actually very little to no erosion on Venus. The only type of volcanism we have is volcanism. The only type of geology we have is volcanism. On the other hand, if you added atmospheric circulation, that would create some wind erosion. So with a rotating Venus, Andrew, you'd be correct.
All right.
The magnetic field would also protect your water. And I remember us needing water for one of our other geological processes. If you could condense just a little bit of liquid water onto the surface of Venus, I almost might suspect that there might be some other type of geology that could develop.
Plate tectonics.
Remember that plate tectonics require liquid water. If you could cool off Venus enough for some of the water to condense, who knows? Maybe you could have some continents and some plate tectonics. It would certainly mean a cooler Venus. Let's try to put all this together into a conceptual answer. If Venus had rotated as quickly as Earth, we would expect its geology and its climate to change in significant ways. Wait, it's CANT, right? Man, my spelling is not what it should be.
Is that it?
Yeah, I did do it right this time. Hold on, let me close my tabs. I'm worried it's going to be freezing my internet. Okay. First, rapid rotation would create increased levels of wind erosion and split the atmosphere into a set of, and here's a big concept, triple Hadley cells. Let's underline that because that's a key concept. The Hadley cells would create different temperature zones on Venus, which might allow volcanically outgassed water molecules to condense maybe near the poles. The equator would probably still be too hot. We're going to continue this, but let's make sure you got this much. I'm going to sort of try to continue up here. I'm going to erase the first 2 or 3 sentences. Rapid rotation would also kickstart Venus's planetary magnetic field, which would further protect outgassed water molecules from so-called solar wind harassment. I might have too many R's in harassment. God, my spelling is atrocious. Yeah, I have too many R's in harassment, sorry. Andrew, can I erase some of this bottom stuff? Where are you right now, buddy?
Yeah, I'm up top. I'm up
All right,
top.
so I'm gonna kill all this down here. I need space. If temperatures at the poles were cool enough, it might be possible to trap some of Venus's excess CO2 on a polar seabed. Mars clearly at one point had a polar seabed, so it's not outrageous to think of that. On a polar seabed, resulting in cooler global temperatures. All in all, a swiftly rotating Venus would have had a cooler climate, although, I don't know how I want to say this, although probably not as cool as Earth's. Although not, and we'll use the double entendre there. So Venus would have been a more likely place for life to form had it rotated rapidly. You can see the powerful effect that rotation has in the development of a world. And as Jake said earlier, in a messed up way, magnetic fields are good for life. In a complex thinking way. that was our big word question, or one of them anyways. So I wanted to kind of crank that out quickly. Andrew Bates, why don't you call up the questions? I'll have you read the next one. And Andrew Larson, you let me know when you're done writing.
All right.
Has anyone been outside today? It looks sunny out there.
It is, but it's cold.
Not
Windy.
where I am.
Yeah. I haven't.
Windy.
Wait, where are you, Jake?
I'm in Mass.
Oh, geez, I didn't know you were up there. Have you
Yeah,
been?
it's like really cloudy.
Okay, well, maybe it's going to shift its way down here. I've got to I actually have to go into CCRI today to get my my course evaluations. By the way, I should mention this to the whole class. Please make sure that at some point you do the student instructor evaluations. You know, you have a chance to evaluate me and say the good things and the bad, whatever you have to say. Last semester, because of COVID, or I think in the spring, one person from one of my classes reviewed me. It was just one person, so and I don't think they liked me very much. So if you, especially if you liked the class, say something nice about me.
Where can you find it? Because I remember last spring when I took your class and I didn't see it at all on Blackboard or anywhere.
Bella, the way I of course have professor view, so I'm not sure, but I suspect it's probably the same. When I go to my CCRI, where is my CCRI?
Brendan, I'm all done.
Okay, thank you. Let me show you guys where I think it will be. I have to go to the for faculty tab, and then I go way down here and it says student ratings of instruction, right? So I'm like, usually people enjoy my class pretty well, but I noticed in fall 2020, when I was looking at them, oh, this was a good one. There was one class, look at the total respondents. It's like 2 people, 1 people out of 25. So I was like, all right, well, you know, maybe I should make a pitch for that. So I suspect at your My CCRI, it would be similar down in the right corner there in the for student tab, okay?
Okay, thank you.
Yeah, Bella, go ahead and review me, okay? It takes just a second. And you could do it sometime between now and the end of the semester. I'm gonna erase, guys. Is everyone good? Speak now, forever hold your peace. Sorry?
I'm all set.
All right. Andrew Bates, so you want to read us 57?
57. Feedback processes in the atmosphere. As the sun gradually brightens in the future, how can the CO2 cycle respond to reduce the warming effect? Which parts of the cycle will be affected? Is this an example of positive or negative feedback?
So believe it or not, stars over long time scales slowly become brighter as they evolve towards red giants. You might have to take my astronomy 1020 class to learn more about that. Now, the sun's not getting significantly brighter in a day or in a 100-year period, but over hundreds of millions of years, it does a little bit. And that means even without man-made contributions, which are much faster, the Earth will brighten over time. There are ways of thinking called systems thinking, where you can develop positive and negative feedback cycles. You've probably heard these terms before. An example would be a population of deer on an island off the coast of Maine. The deer have no natural predators in the form of wolves, so they begin to breed and multiply. But as they continue to strip bark and eat the trees, they eventually exhaust the food supply, and the herd is naturally culled due to lack of available resources, and that's considered to be a negative feedback loop. Earth's CO2 cycle can function in a positive or negative way, depending on how hard you push it. But if you push it only gently, it is possible for a negative feedback cycle to develop. And what the book is referring to, I want to show you. There's a classic picture here. I have it in my slideshow called The Earth, of how the feedback cycle works. So this is basically a riff off of the CO2 cycle, which you guys learned about in our last lecture. And I think it was Jake who today perfectly summarized it from memory. You've got volcanic outgassing, CO2 dissolves in rainwater, rain washes down on the plains of Spain, the silicate rock plus the CO2 plus the water form carbonate rock, and they get pushed along the seafloor bed. Well, here we can imagine a set of feedback cycles. I don't know if you guys know this, but we have recorded the history of Earth's temperature through ice core drilling. Basically, in Antarctic sheet ice, little bubbles of atmospheric gas and CO2 get trapped in these ice sheets on Antarctica. So scientists can drill ice cores out of the Antarctic pack ice, and they can go down through like layers on a tree ring through geological layers of ice, and they can analyze those little bubbles of trapped gas and figure out how Earth's atmosphere changed over time. Because of this and because of other factors, we know that at times in Earth's history that Earth has gone through what's called these global ice ages, and may have even dramatically went into a snowball Earth phase where ice caps advanced far enough down the lines of latitude to almost cover the Earth in a global sort of ice sheet. And we know that Earth has recovered from such global ice ages. And the idea goes something like this. When Earth went through an ice age and it became too cool, well, you ended up dissolving less CO2 from the atmosphere, and the volcanoes keep pumping out carbon dioxide, and we created a mini excess greenhouse gas effect like on Venus that eventually over long time scales warmed the Earth back up. In this one, we're asked to follow this trail of the feedback loop, where the sun is going to brighten up Earth, it's going to increase the warmth. The extra warmth and the extra precipitation will involve more dissolving of CO2 from the atmosphere into rain droplets. Those rain droplets with more enriched CO2 will pull more carbon dioxide out of the atmosphere and form extra carbonate rock on the seafloor bed. This will remove the small concentration of CO2 that we have and create a weaker greenhouse effect, which will cool Earth down. So that we don't end up writing another epic paragraph, I think we can summarize the answer to this in a set of logical bullet points. And that's how we're going to formulate this so that we can go through the steps in our mind of the feedback cycle. So the sun brightens, and this leads to warmer global temperatures. That's the first step in our reasoning. I'm going to kind of reset my register and start back over here. In the next phase, increased temperature will dissolve more CO2 into rainwater and other forms of precipitation. In principle, maybe, I don't know if it dissolves into hail or ice as well, but rainwater is probably the best way. And CO2 will also dissolve directly into the oceans. Increased CO2 in the oceans okay, my English is failing me here today. My grammar is failing me. Increased CO2 levels in oceans form more carbonate rock. That's the term you were looking for today, Jake, was carbonate rock. Reduced CO2 levels in the atmosphere trap less infrared light, which essentially means weakening the greenhouse effect. And a weakened greenhouse effect will lower global temperatures. This is an example of a negative feedback loop.
You lower that a little bit, Brendan?
Yep, sorry. You guys are able to read that okay, right?
Yeah.
Oh, Joel, I didn't get to read that article yet because I had to talk to some people during the break there. I got a little distracted. I'm gonna check that out while you guys are writing. I noticed it had to do with neutrinos too.
Yeah, I noticed that seemed interesting to me because neutrinos are like the super, like, if I remember right from 1020, those are the things that they know are there, but they can't see or measure them, right?
Right. Well, they do measure them. You know how I talked about those ice cores? Today, the world's most powerful solar neutrino telescope is called IceCube, and it's located in Antarctica. Neutrinos are created during nuclear reactions. They're basically created when you transform a proton into a neutron. And neutrinos are so light in terms of mass that they can pass through most atomic matter like ghosts, like empty space. They are ghost-like particles.
Yeah.
And literally, if you create a neutrino inside the core of the sun, it can travel through the entire sun without hitting another atom or particle. The sun is transparent to neutrinos, and the Earth is partially transparent to neutrinos. We detect them when they interact with ice, deuterium in the Antarctic ice. And it's a way to kind of directly measure the rate of nuclear reactions. Now, from what I read in that opening paragraph, I teach you guys in our lectures that the sun creates energy by the proton-proton chain. But there are other branches of hydrogen fusion that you didn't learn about because they're kind of above your pay grade. There's a second branch and a third branch of the proton-proton chain. I suspect that the point of this article is that the sun is actually using multiple different branches of the proton-proton chain to generate energy. That's what I think the point is. And that is something directly related to what we learned about. Hey, I want to make a point about this negative feedback loop. Someone might be tempted to say, well, hey, man, can I just run my air conditioner and spray the deodorant and just crank my gas guzzlers without worrying about it? Who cares if humans are heating up the planet? We got the CO2 effect. Well, hold on a smokes there, partner, before you get too carried away. Yes, the CO2 cycle can help restore equilibrium temperatures on Earth. But you got to think about two things when you add man-made levels here. The CO2 that's being pumped out in the natural process is coming from volcanic outgassing, and it constitutes only 0.04 or, sorry, yeah, 0.04%. I was remembering if it was decimal or percent. Basically 0.04, 0.04%, a very tiny amount. Humans are significantly adding to that with their fossil fuel emissions. And furthermore, suppose the CO2 cycle really could solve us. Jake, I asked you this question before. What's the longest time scale involved in the CO2 cycle here? Which part of the CO2 cycle takes the longest?
Plate tectonics.
Right. And how long, do you remember what a geological timescale is like? How long does it take two continents to bash together? How long do you think it'll take the seafloor bed to subduct under that thing?
Like probably more than thousands of years.
Definitely more than thousands. In fact, more than millions. Jake, you'll remember that when we calculated the rate of time since South America collided with Africa, at 3,000 kilometers and 1 centimeter per year, we estimated it had been about 300 million years since those two continents were in contact. And that to me suggests, Jake, that these seafloor beds move over hundreds of millions of years. So Earth might restore itself in 200 to 300 million years. Will you restore yourself in 200 to 300 million years? Sorry, brochacho, you don't have that much time. Because if Earth goes through a major climate change, in 100 years or in a period of less than 1,000 years, all the apex predators are going to get wiped out. And that means you, right? So climate change might be okay for weird little insects and tardigrades and cockroaches and other types of fungi that are just going to survive whatever the hell happens. But it's not going to be okay for you, and probably it's going to be bad for the bunnies and squirrels and doggies and the cute little animals that you do care about. So I would suggest that you do not use this as an excuse to not take climate change seriously. That's my only point, okay?
So with the negative feedback, right?
Yep.
Would that create more volcanism? Or
it's possible that with more carbonate rock, Joel, you would have increased levels of volcanism. That is true.
yeah, that was what I was thinking, because you have more under the surface activity.
So
Therefore,
even us talking about this right now sort of hints at the insane complexity of it. When we listen to these professional climate scientists who make complex computer models of it, we're just kind of scraping the surface at the 101 level. And already we can see, wait a minute, there's more to this story, because that might increase levels of volcanism, and how will that affect things? Also, what if you heat up the planet enough to boil away the ocean? You could then release some CO2. The people who work on this, it's a very complex science. And usually what they do is they make computer models of interacting systems and try to watch the systems evolve. And after enough simulations say, this is what I think will really happen if you add more complexity to the situation. So in fact, yes, Joel, and that's why someone might actually want to study, like a branch of planetary science would be like climate science, right? There are climate scientists who make a career analyzing 6 ways to Sundays, these very complex problems. It's very difficult when they get distilled down to the public, because most people are not even going to college like you guys are and learning about the fact that there is a CO2 cycle, you know? So you've taken your first step into a larger world by thinking about these things. But yes, Joel, and I'm not exactly sure how that would add to it. I think that would add another layer of complexity. Anyways, why don't we move on? Let me go back to my main view here. Let's move on to 61. The rest should be mathematical. Oh, looks like those clouds are moving in on us, Jake.
yeah.
Yep. Wow. That was fast. That was really fast. Okay. Andrew Larson, do you want to read a problem?
Yeah, I'll read.
Okay, it's number 61.
Oh. All right, the mass of an atmosphere. What is the total mass of Earth's atmosphere? You may use the fact that 1 bar is pressure exerted by 10,000 kilograms pushing down on a square meter in Earth's gravity. Remember that every square meter on Earth experiences this pressure from the atmosphere above it. Alternatively, you may start with the English unit value of pressure of 14.7 pounds per square inch and convert to kilogram for your final answer. Remember that the surface area of a sphere of radius r is 4 pi r to second.
Okay, this problem probably seems wicked complicated at first, but it's actually so simple. And I think we could help ourselves out by drawing a visual picture of what's going on here. So let's draw the Earth. Radius r. And you guys know that the radius of the Earth is 6,400 kilometers, right?
Yes.
Okay. Now imagine the atmosphere of Earth is a gas surrounding it. I'm going to exaggerate. The atmosphere of Earth is wicked thin in comparison to its radius. Like, let's look at a picture of Earth from the ISS, just to remind you here. So I just want to show you that I'm exaggerating this. Look at, compared to the radius of Earth, look at how thin our atmosphere is. It's a microscopic fraction of the radius of Earth. Well, we know it only goes up about maybe 400 kilometers at best, right? That's maybe not microscopic, but that's a small percentage. Allow me to exaggerate for a second so that we can try to think about what's going on here. So I'm going to surround the Earth with an atmosphere. And what the book is asking you to do is to consider a square meter column. So imagine we took a square, roughly the size of my chalkboard here. You can see that my chalkboard is pretty darn tootin' close to 1 square meter. And then we made a kind of, do you guys know what they call a 3-dimensional rectangle? They call it a parallelepiped. One of my Italian physics professors used to call it a parallelepiped. Okay, so a parallelepiped. Okay, every time I say that word, I think of parallelepiped. And so we're going to imagine, let's see if we can draw this with our best 3D skills. So here's a 1 square meter rectangle, and then it's going down to the ground like so. That's the best I can do 3-dimensionally. And that wasn't very good either. And we're just basically imagining that this rectangle is creating the pressure. Now, you guys know that the way they did this here was a little bit goofy. We know that 1 atmosphere of pressure is equal to 100 kilopascals. So how many pascals would that be?
$100,000.
Kilo means 1,000, so that's 100,000 pascals. But do you guys remember what the definition of pressure was, or what a pascal is equal to in more fundamental units? 100,000 pascals is 100,000 newtons per meter squared. But a newton is mass times acceleration, right? So this basically means mass times little g per square meter, where I'm using m for both mass and for square meters. That kind of sucks. Actually, let me put my units in blue so I don't do that. I'm doing something kind of wacky here. And when I get wacky, people get confused. Newtons per meter squared. Please notice that black is variables and blue is units. Now, do you guys remember what little g is? Little g is 10 meters per second squared. Sorry, yeah. And mass is in kilograms. And that means the mass per square meter is 100,000 divided by 10, or 10,000 kilograms per meter squared. That's how they derived that. So I'm basically showing you where they're getting the mass of one of these columns of atmosphere. And that mass is just the mass of 1 parallelepiped worth of atmosphere. So what do you guys think we should do if we want to get the mass of all of the parallelepipeds in kilograms? What should I do next?
multiply by 6,400.
Not
Or-
6,400. You want an area. If we multiply by the surface area of Earth,
Oh,
we'll be multiplying
four-
by all the parallelepipeds, right?
yeah. So 4 times pi times 6,400 squared.
Well, we have to be careful here because this is in
Or-
meters squared and that's in kilometers. So
Oh, yeah. So 6.4 times 10 to the 6.
yeah. So we know
Okay.
that 6,400 kilometers is 6.4 million meters. That's because of dimensional analysis. So the total mass of the atmosphere will be 10,000 kilograms per meter squared times 4 times pi times 6.4 million meters squared. Hey, do you think the Earth's atmosphere is a significant fraction of its mass? Yes or no?
Yes.
If you had to take a guess, what percentage of the mass of Earth would you say the atmosphere is?
One 1/16.
I'm sorry, Joel.
It's 1/16.
You think the
Because the
atmosphere
atmosphere.
is 16th of its mass, which is what, 8%?
Well, I was thinking the distance, but
Yeah, but that's not the same thing as mass, right?
no.
Anyways, can you guys calculate that for me so I don't have to? Come on, you stoopy. Okay. 1/16 is 6%, by the way. You're right. 64 over 400 over 64 is 1/16, Joel. Very good of you. But no, you're going to be surprised. One sig fig is fine. How many trolls are out there today? Let's see the troll. I hope you're
Cycle-
calculating trolls. You know what I think I'm
Cycle-
going to do? I think all the trolls are going to have to take the final exam, and all the video
Oh,
can use their midterm grade.
ouch.
Look at this.
How many people turn their cameras on?
I think if you're a troll, then you're not. Then you have to take the final exam. All right.
I don't really count Cam as a troll because he's 90% had his camera on the whole time.
Yeah, my camera's so great.
Nice, Enrique.
All right. All right. So what do we got here? Should be pretty simple, right, for you guys?
Jake, you got an answer?
Don't be calling on me like that. I have an
Well-
answer.
Well, with the
Right.
English stuff, you're good with it. Explaining the carbon dioxide cycle, you're
Yeah, he was
that's
right
'cause
on
it
that
doesn't
today.
involve
you
math.
spit it out like you were farting.
It doesn't involve math. That's why.
I know.
All right, Jake, let's hear your answer. One sig fig.
Well, from what I got, it looks like 251,327.
All right. Punch, do this in memory of me, okay? Just
I'll do
use-
my best.
Okay.
I got 5 to the 18th. 5
Yeah.
times 10 to the 18th.
Paul, let's just do this for Jake. You got 10,000 there?
Okay.
Yeah, I got 10,000.
Cam, that's a little off. Times 4
Yep.
times pi times 6.4 exp6. Now you got to square that. And now you got to hit equals.
Okay. So
You might
I
have
added open parentheses and then couldn't figure out where the square button was, so I did exp2.
Oh, no, that means times 10 to the 2. That's not the same thing at all.
Well, exactly.
The correct answer is 5 times 10 to the 18. What are the units?
Kilograms.
That's right, because the meters squared cancel out.
And that's mass.
Yeah. Just for fun and giggles, let us see what percentage of Earth's mass that comprises. The percentage of the mass of Earth is 5 times 10 to the 18 kilograms divided by the mass of Earth.
6 times 10 to the 24.
That's great.
Yeah. I
right.
remembered something.
Huh?
I remembered something.
I got 8 times 3 times 10 to the minus 7, which is 8 times 10 to the minus 5%. 0.00008%. So, Joel, does the mass of Earth's atmosphere comprise a significant percentage of the mass of Earth?
No.
No. It's like nothing. It's funny, you look up at that big sky, you breathe that lung full of air. It sure seems like there's a lot of it out there, but it's a microscopic fraction of the matter that makes up Earth. Pretty wild, honestly. Andrew, let me know when you got all this.
All right.
You're good?
Yeah.
All right. Two to go, guys. 2 to go. We're making progress. Cam, now that you're back on cam, could you read us a problem? Are you down to do that, buddy?
Yeah, let me just put on the website. I'm gonna log in quick.
Okay. Yeah, I can't think of a better way to do this. Let me hide the trolls again, because
Okay, it's logging me in.
okay. Oh,
Go to
we're
courses.
so close to the end of the semester, guys. We just got to hold on another week, right?
Mm-hmm.
How was your first fall semester completely online? Show of hands, how many of you were taking more than just my class? How many of you were taking multiple classes? Did you guys find that stressful to manage all of those courses from your bedrooms?
Oh
Yes.
yes.
Absolutely.
I'm already failing one class.
Wow. Well, you're not
That's
feeling
how hard it is.
You're not feeling mine.
I'm-
I bet, like, I'm
That's
trying
good.
to, you know, this is so weird. I'm 45 was tough, Zach. I bet, Jesus. Plus, some of you guys are working too on top of it, and you're probably going nuts. You know, I'm 42 now, so I thought I had kind of seen it all, but the pandemic is just a total new twist on life. I
Yeah.
bet through was bad, fellas. So I was trying to imagine if I were you guys and trying to manage all this from the bedroom. That might have been pretty weird, right? You probably have a new appreciation of why going into school is kind of good. It kind of like separates things a little bit, you know. I know it's weird for me here. It's like I'm looking at dust bunnies under my rug, and people are texting me. It's kind of cool in a way, but it's also distracting, you know. So you guys felt like it. Did anyone feel like it worked for them, or was it mostly not good?
Not good for me.
Yeah.
But
It wasn't good for me either.
All right.
The class
I didn't.
teachers don't even bother participating into helping. When you ask
I,
questions, they just put you in like figure it and mold yourself.
Wait, say that again, Bella, because I'm really curious about what you guys have to say. What did you say about the experience?
So like I had not this semester, the teachers were pretty good with it, but like when we switched over in spring semester, my computer teacher was like non-existent.
That's terrible.
Non-existent. Yeah, she was like take class, she switched from Zoom to Blackboard, and then when you couldn't get in touch with her, it was so bad. So bad. And like when you try to ask her a question, she said, well, it's in the book.
Yeah, see, that's not right. I believe that the only mistake you can really make as a teacher is just kind of not being there. You know, it's kind of like probably, I'm not a father or anything, but I imagine if you were a dad or a mom, you just have to kind of be there for your kids. You don't have to do it perfect. You just have to be there. So when people, I'm not going to say I've never missed an email from a student, but I try to respond to them. And I try to spend this time with you guys because I think that's what makes it. A big thing that I'm going to wrestle with in my next semester, because we're doing spring online, is I've got all these recordings made and I'm pretty proud of the lectures that I've done. I could just deliver it to the students as YouTube videos, or I could take the time to kind of do the whole song and dance with them again. I don't know if you guys have thoughts about that. I'd be interested.
Both. Like
both is the best of both worlds.
Like when I mean both, I meant like give them the choice of seeing you on a set schedule. So if they do have questions, they can do a video meeting with you, so they don't feel like, okay, he's just sending videos to us. Because you're the, like, to be honest, you're the best teacher I've had so far in CCRI. Like Jay, that's why I took this course again.
That's great. No, I agree.
I agree too.
That's great, guys.
You help us with the homework. You help us, and if we have any questions, you're always there answering. Plus, you're funny and all that stuff. Yeah. But
I think it's actually more fun to do it together than it is to do it alone. You know, like I think it's,
maybe
a very rich
like
experience.
I would say just help out with a meeting and stuff like that with the homework, because the homework is more difficult to understand even through videos.
Yeah, maybe I've got to do something live because I'm worried if I just deliver the YouTubes that no one will get in touch with me and I'll become divorced from everyone. I don't want that. So, all right. So
without the Zoom class, the online Zoom classes, I probably would fail this class too.
Because you'd just be punched out, right? You wouldn't be doing it.
Yeah.
I'm worried about that. It's kind of terrible. We have to all torture each other by being in the same place at the same time a little bit, right? That's that's the glue that binds this thing together. Some of the night students are actually handling it very well. They're under very rigorous time schedules where they have to work during the day. And some of them, I'm very impressed with the night students. If you guys are out there listening later, very impressed that many of you kept up with these assignments, even though you're not here live. Sorry it couldn't be that way, but in any case, it is possible, but it is tougher, I think. Okay, so let's not drag this out too long. Let's get on to number 62. All
right.
Cam.
I was reading it. Yep. The role of reflectivity, by assuming 0% and 100% reflectivity, respectively, find the maximum and minimum possible quote unquote no greenhouse temperatures for a planet at 1 AU. What reflectivity would be necessary to keep the average temperature exactly at the freezing point? Compare this value to Earth's actual reflectivity in table 10.2.
Okay, this is 3 mini problems in one, but they're not so bad once you get into it. This is about the no greenhouse temperature. The no greenhouse temperature tells us that the temperature of our rock in space, before you account for the greenhouse effect, is 280 Kelvin times the 4th root of 1 minus the albedo divided by the distance squared. So the maximum temperature, if you think about it, how does this work? Black absorbs sunlight. As you know, if you wear a black shirt in the summer, you get hotter than if you wear a white shirt. So the maximum temperature a planet could have would be if that temperature was jet black, like even darker than the surface of the moon. In fact, this is what we mean by a black body. It is a perfectly absorptive substance. And that would mean that albedo was 0 because albedo tells you your percent reflectivity. On the other hand, a minimum temperature would be a white planet with 100% reflectivity. That might even look almost like a disco ball, a perfectly white planet. Or I guess it could be white, but just scatter all of the light back. It would look like a bright glowing ball. We'll deal with the albedo to be at the freezing point a little bit later. First, we can crank out these first two problems quite quickly and quite simply. So we know that the distance is 1 AU. And remember that AU, thankfully, are the units that we can use in this cook the books formula. So for a black planet, we will have a temperature of 280 Kelvin times the fourth root of 1 minus 0 divided by 1 squared. And can you guys look at that and evaluate that pretty quick? What will that turn out to be?
$280 Kelvin.
Yeah. And this is where the 280 Kelvin comes from in the no greenhouse temperature. The 280 Kelvin,
Jake,
I call it a reference temperature because
Jake, it's all ones inside that
Talk to
square.
me.
right.
It's all ones inside that square.
I would have gotten it eventually.
1 minus 0 is 1. 1 squared is 1. 1 divided by 1 is 1. The fourth root of 1 is
I was
1.
going to say 0, so I was on the same.
Jake, we'll try you on the next one.
Yeah.
No.
280 Kelvin is the temperature of a perfectly dark absorptive substance at 1 AU. Okay, let's try the white planet now. A white planet has a temperature of 280 Kelvin times the fourth root of 1 minus 1 divided by 1 squared. So Jake, what would that be?
Is it still 280?
No,
Yeah, of course not.
of course not. Think about it.
1 minus
slowly.
1 is 0 divided by 1.
What is
0.
0 divided by 1?
0.
You just, yeah. You
And
just
what's
said it.
what's the fourth root of 0?
0?
What's 0 times 280?
0.
So that's your temperature.
Oh. Same track. I'm almost there.
If you had a perfectly white planet, its temperature would be 0 Kelvin. Isn't that weird? It couldn't have, if you can't absorb any photons, you can't get hot. Okay, once you guys write all that down, we're going to deal with the third one, which is a little trickier. Andrew, let me know when you're kind of all cut up there.
All right. I'm all set.
All right, I'm going to erase a little bit of this. Okay. We want to know what albedo would Earth need to be at the freezing point. Do you guys think we should use the 273 Kelvin or the 160 Kelvin from today's lecture? Which temperature should we use for Earth to be at the freezing point?
$273.
Yeah, I would say so, Mateus, because, or what, is it Mateus or Mathis? Why am I always saying this wrong?
So my name is actually in Portuguese. I usually go by Matt because it's easier, but either or really.
But I want to know the real one. Could you just say it?
Mateus is my name.
Mateus. Okay, I like Mateus. It sounds cool. I just sometimes start to, I get paranoid because I said it wrong once. And all right, Mateus. Mateus, I would also choose 273 because even though this is the no greenhouse temperature, I want to assume that it's freezing water under the atmosphere of Earth. So I like what you said there. So we're going to set the temperature to 273 Kelvin. And that's the freezing point of water. And that's equal to 280 Kelvin times the fourth root of 1 minus the unknown albedo, but we know that it's 1 AUA, so that's 1 squared. Let's do the same thing I did earlier. Let's divide 273 by 280. The kelvins will cancel out. And then, to speed things up, I'm going to raise both sides to the 4th power. And because it's just a 1 there, that's equal to 1 minus the global albedo. Do you guys know how to solve for A here from your algebra class? How does one solve for A here?
You add 1 to the other side?
That won't help you, because if you add 1 to both sides, you'll get 2. 1 plus 1 is 2, and you'll get a plus 1 over here. Try again.
That's the only one of the tries I have.
No, come on, you got another try here.
I thought you always had to like get the variable alone. So
You do, but if it's
So
1
what,
minus
you
A,
give it-
that doesn't help you there, does it?
Oh.
Watch.
No.
I'm going to add 1 to both sides, like you said. 1 plus 1 is 2. I now have 273 over 280 to the 4th power plus 1 equals 2 minus A. That didn't exactly help you, did it? That made things worse. Try again.
Yeah, Joel, what do I do?
I don't know.
Well, if you added 1 to 1 and that makes 2, how do you isolate? Oh,
Wait, was it just subtract?
yes,
Yeah.
because you have to
You also
cancel
said
it. You have to basically cancel it.
Well, I had the right idea.
You've got to add something to both sides, but it's not 1.
So if opposite of subtract is add, but you have to add the negative.
Right,
So-
so keep going.
So you subtract 1.
From both sides. All right, let's try that. Now we have 273 over 280 to the 4th power minus 1 equals, oh shit, now we've got negative A.
And divide by -1.
Or multiply by negative.
Multiply, yeah.
So that will make this positive and that negative. So A is equal to 1 minus, nuts. 1 minus 273 over 280 to the 4th power. Let's see if we can do that without screwing up. 1 minus, oh, sorry, things aren't working here. 1 minus, open parentheses, 273, divide by 280, close parentheses, to the power of 4 equals. What you got?
.1.
Well, we should really just round it to, 0.09, which is really close to.
And what?
Fine.
What did I do? I got 6.3 to the -3.
You didn't use parentheses or order of operations. Let's do it again, Joel. Ready? 1 minus, open parenthesis,
Yeah, 273,
273,
280.
divide by 280. First, we close the parentheses.
Yeah.
But now we have to raise it to the power of 4. To the power.
Oh, I hit shift instead of.
Oh, you took the 4 through. Yeah, okay.
Oh, doggone it. Okay, that's what I did.
Really, really close to 10% reflectivity. Now, they asked us, Cam, remember, they asked us in the problem to compare that to Earth's global reflectivity. And I have that in one of my slides. I have that here in slide 41.
Is that 12%?
The average albedo of
Oh,
Earth,
31.
according to this slide, is about 30%. So basically, if we are basically 3 times over the freezing limit. So if Earth was 1/3, this is 1/3 of Earth's current albedo, If Earth was 3 times shinier, we would be at the freezing point and probably go towards a snowball Earth. The reflectivity of Earth actually has a impact on how much heat we can absorb. That's a scary thing about a snowball Earth, is that if it was covered in ice and the ice was shiny, you might actually lower temperatures even more and create a negative, positive feedback cycle. Excuse me. All right. 62 down the hatch. One last one to go. It's kind of a doozy, though. I'll try to be fast here. With everyone's permission, I'm going to erase now. Enrique, you made the mistake of sharing your video with us. That means you get to read a problem. I'm going to squeeze a little out of you today. Oh, yeah.
Did he disappear?
God. Got to earn that, missing that final exam by. Do you have them questions open?
I do.
All right. So why don't you read us 65?
Okay. It's escape from Venus.
Okay.
A, calculate the escape velocity from Venus's exosphere, which begins about 200 kilometers above the surface.
Okay, I'm going to stop you there, bud. Because this is 3 kind of juicy parts, let's just read one at a time so we don't forget what we're doing. So they want to find the escape velocity of Venus, but they want to start not at the surface, but did you say 200 kilometers?
Yes.
Okay. And that's 200 kilometers above the surface. That's the height. That's pretty funny because our exosphere probably starts at like 300 kilometers. I didn't realize that Venus's exosphere was closer to the planet there. Well, actually, you know what? I'm starting to wonder what the hell I know after all. I have a graph here in slide 5, I think. Actually, I guess that's probably similar for Earth too. The thermosphere starts around 90 kilometers. So I bet 200 kilometers is comparable for our, what does the cartoon from our book say? I hope they tried to get it right. Yeah, they have the exosphere starting before 120 kilometers. Okay, wow. All right, I just learned something myself. Okay, so let's draw Venus. I know the radius of Venus for you guys. It's 6050 kilometers. It's 6050 kilometers. We've got to convert so that the particle is above. The particle is trying to escape. So this is 6050 kilometers. And the particle is 200 kilometers above the surface, right? So the full height, the radius plus the height, is 6050 kilometers plus 200 kilometers, and that equals 6250 kilometers. And we're going to need to put that into meters, so I'm going to do dimensional analysis. I'm going to multiply by 1,000 meters per kilometer, and that gives me 6.25 times 10 to the 6 meters. I sped through that part because that's just dimensional analysis. You guys know how to do that. The escape velocity of Venus is radical 2 gm over r. By the way, I do have this problem, one almost identical to it on my final exam. So if you are going to take the exam, you're going to have to be able to do this. Okay, we know what G is. Big G is always 7 times 10 to the negative 11 meters cubed per kilogram per second squared. You know, another nice thing, if we decide not to do a final exam, but if we just double your midterm grade and use that for your final, those of you who are failing another course like Cam or doing badly in another course, Cam, maybe you can turn it around with a little extra time at your disposal. I would hope so, that you could do a Hail Mary pass. Try not to fail that class if you can, Cam, okay?
I'll try not to, as long as I can remember, since there's no online class meetings like this one.
Right. No, I can see that. Look, I've been a procrastinator all my life. I've got a big project hanging over my head right now, so I haven't changed a bit since I was a student. I know how you feel. All right, let's the mass. I know the mass of Venus. It's like 5 times 10 to the 24 kilograms. So let's just get to this. So the escape velocity is the square root of 2 times 7 times 10 to the minus 11 meters cubed per kilogram per second squared, okay? The mass of Venus is 5 times 10 to the 24 kilograms. All divided by that height of 6.25 million meters. Why don't you guys see if you can crank that out for me? Joel, could you round that to 2 sig figs?
Yeah.
What you got?
I was waiting for everybody else to kind of get there.
All right. We could try that.
I'm a
If
little
we get
quicker
there.
a little quicker at the number punching.
Yeah, it's amazing what 2 semesters of training will do. I bet Bella has the answer. Maybe.
Yeah, she's trolling you.
He's trolling. Okay, Joel, what do you got?
11,000.
Did you get 11,000?
Well, it's 10,583.
Oh, wow. Okay. Fine.
So since it's basically 10,600, it's you round up to 11,000.
Yeah, I wonder if we use 6.67 there. I'm worried that we're getting the same number as Earth. It should be a little bit tiny. Let me just
Yeah, that's what I noticed too.
Well, because they're so similar, right?
Yeah.
They're sister planets. Let me see if I use 6.67. I don't think it's going to change that much. Wow, this calculator's getting messed up from all the dry erase marker. Yeah, unfortunately, rounding this to 7 kind of jacks us up a bit. The number I got when I used 6.67 is basically 10,300. So guys, just for kicks and giggles, I want you to change that to 6.7. Normally, one significant figure of G is good for us, but here I want a little extra precision. What are the units there?
Okay, so meters squared. So
Kilograms cancel.
it's meters squared over meters per second.
Yeah, because it's the square root of meters squared per second squared.
Yeah.
Meters per second. Box that. That's the answer to part A. I had to use the extra precision of G so that it would come out a little bit less than Earth's. Just a tiny bit. Okay, when you guys are ready, I'm going to move on to the next part. Andrew, give me a shout when you're done.
I'm done.
Oh, okay. Everyone, I'm erasing. Okay, Enrique, can you do B for us? Read us, B.
Calculate and compare the thermal speeds of hydrogen and deuterium atoms at an exospheric temperature of 350 Kelvin. And then the mass of a hydrogen atom is 1.67 times 10 to the negative 27.
That's kilograms, right?
Yep, kilogram. And the mass of deuterium atom is about twice the mass of a hydrogen atom.
Because deuterium has 1 proton and 1 neutron. So it's twice the mass of hydrogen. Okay, let's remember how the thermal speed goes. The thermal speed is the square root of 2 times the Boltzmann constant times the temperature divided by the mass of the particle, where K, the Boltzmann constant, is 1.4 times 10 to the minus 23rd joules per Kelvin. And joules per Kelvin is the same thing as kilogram meters squared per second squared over Kelvin. People usually write it as joules per Kelvin because they don't feel like writing all of that garbage there. It's too much. I'm going to wait till you guys finish because I kind of need to erase and do 2 halves of the board here. So I'm going to wait till you guys catch up to me. All right. How do you guys feel about me erasing now? Is that good? Yep. All right. Okay, I wanted to erase so that I could have a lot of board space here. Let's do hydrogen on one side. I forget what they call this style, but the text in the Bible has this what is it? Dual column style. Hydrogen versus deuterium. And we'll try to calculate the thermal speed on each side for hydrogen versus deuterium. So for hydrogen, we have the thermal speed is equal to the square root of 2 times 1.4 times 10 to the minus 23rd. That's joules per Kelvin. Now we have to multiply by the temperature of, was it was it 300 Kelvin, Enrique?
Yes.
All right, 300 Kelvin. And then the mass of a hydrogen is 1.67 0.67 times 10 to the minus 27 kilograms. Let's do this factory style. Let's set it up for deuterium. Deuterium is the same thing except for twice that. For deuterium, 2 times 1.4 times 10 to the minus 23rd joules per Kelvin. Same temperature, 300 Kelvin, except now we're going to have to multiply this by 2. And I'm just going to leave it alone there. I'm going to do 2 times 1.67 times 10 to the minus 27 kilograms. Our answers should come out in meters per second because they're velocities. What I want you guys to do is to calculate the thermal speed for hydrogen and then calculate the thermal speed for deuterium as best you can. I'm going to get some iced tea. When I come back, I want those numbers. All right. Talk to me. Who's got some stuff?
Yeah.
Jake, what's your power there?
-7.
That's too small.
Sounds good.
Can you type it again? You must have made a typo somewhere.
Yeah.
2 times this times that, divide by that, equals then square root. Anybody else? You got something, Andrew? Bates?
I got 2,242.7.
That's good. Let's round it to 2 sig figs.
$2,200.
Yeah. And what are the units?
Joules over kilograms.
He's speaking, but we can't hear him.
Oh, joules over kilograms.
Radical joules over kilograms. But a joule, remember, is a kilogram meter squared per second squared per kilogram. So what do you get if you square root that?
For well, meters and seconds.
That's right. So meters per second,
Meters per second. Sorry.
which is a velocity. So Jake, did you figure out what you did wrong?
No, I got the same number.
Okay. So why don't we punch together then? Just follow after me and you'll learn how to do it right. 2 times 1.4 exp negative key 23 times 300 divide by 1.67 exp negative 27 equals then square root. Shift.
Oh, I just square rooted first.
No, 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 no. You can't. You have to screw it at the end for order of operations. Cam, your
Well, I
number.
mean, I didn't hit the equals button before I square root it.
Cam, why is your number whack? Type it one more time, Cam. How about deuterium?
When I got 1,585, so just round that one to 1,600.
Okay, can someone else verify that?
Yes.
Okay. Cool. Well, if two people get the same answer, I trust it more. Units?
Meters per second.
Let's convert these to kilometers per second. Joel, that should be your forte, right?
So 2.2 and 1.6.
Good. I'd like to remind you guys that the escape velocity of Venus was 10 kilometers per second. It's now time for us to apply the test. We have to apply the test for atmospheric loss. And the test is your thermal speed greater than or equal to 1/5 of the escape velocity? For hydrogen, hydrogen 2.2 kilometers per second. What is 1/5 of the escape velocity?
2.
Sorry?
2.
2 kilometers per second. So for hydrogen, 2.2 kilometers per second is greater than 2 kilometers per second. What does that mean for hydrogen gas in Venus's atmosphere?
Going to escape.
Yeah, it will be lost over a geological timescale. Hydrogen escapes Venus. However, deuterium 1.6 kilometers per second. That extra neutron in deuterium slows it down, is less than 2 kilometers per second. So what does that mean about deuterium?
It gets trapped.
Deuterium is trapped by Venus. It remains. This has to do with a famous experiment in planetary science. And Enrique is going to read us part C next. Actually, first, Enrique, make sure you get all that copied down. Catch up to us.
No, I'm up to date.
Okay. Andrew Larson, let me know when you're caught up.
All right.
You're good? I'm going to erase, guys.
Oh, I'm not done.
Okay.
Where's it?
who's going to get that PlayStation 5 and rock away their quarantine? Maybe me.
What?
All my gamer friends are freaking out about the PlayStation 5. They want to play Cyberpunk. I kind of want to play it too.
Oh, video games.
Yeah.
I barely know how to use my phone or my computer.
Well, they're bad for you, but they're also really fun.
All right, I'm done.
Actually, they're not as bad as some of the things I do. So in comparison, they're probably good for me. All right, let's erase this.
I just break stuff.
This is I'm just commenting on the fact that, you know, now with the pause that we're all going through, we all have to resist the urge to go out. There's kind of nothing much to do anymore. Isn't that weird? I used to go out to bars. I used to go to shows. Now we're all just chilling, you know? Anyway,
That means you get to ride your bike more.
that's true. I always ride my bike a lot. I ride my bike to the bar, you know? Let's erase this and let's do part C. Last bit. Okay, Enrique, what's it say?
Okay. In a few sentences, comment on the relevance of these calculations to the questions of whether Venus has lost large quantities of water.
Now, if I were you guys, I might not be sure what this thing is driving at, although I did suggest a little bit about this today. Why would differences in the escape velocity, or why would differences in the thermal speed of deuterium versus hydrogen suggest that Venus has lost water? This is kind of related to, remember how I told you that they were testing comets to see if their ice had the same chemical composition as the oceans? There's this thing in outer space in the Proto-Solar Nebula. It's called the cosmic abundance of deuterium. And if you kind of look around into outer space and count the number of hydrogens to deuteriums, in outer space, and presumably in the formation of our solar system, there are 6,000 normal protium atoms, 6,000 normal hydrogens to every one deuterium. And we find that in, well, sort of in seawater, but we definitely find it in comet ice. We find it in the interstellar nebulas that we see in outer space. You guys will remember that we actually did succeed in landing a spacecraft on Venus. Well, the Russians did, to be fair. They landed the Venera 12 and 13 missions. And remember, this was a week or two ago. But I showed you a picture of Venus with its yellowy cloud tops. And then I showed you a picture of the Russian, I can't remember now if this was Venera 12 or 13, but I thought it would be cool for you guys to look at it because it's kind of retro and you can see this satellite that was clearly built in the late 70s or 80s, kind of has that look to it. And remember that they sent it to Venus and dropped the spacecraft down, and they famously got those two pictures of Venus, right? They got this picture here, this picture there of the slabs of volcanic rock, and this picture of the front of the spacecraft disintegrating in the hostile environment. But they did something else during the descent, guys. During their descent, they were sampling the chemical composition of Venus's atmosphere so they could figure out what the hell was going on with Venus. And wouldn't you be surprised, but the Venera missions discovered that on Venus, the abundance of deuterium was not 1 out of 6,000. It was a factor of 100 times greater. 1 deuterium for every 60 hydrogens, 100-fold increase in the abundance of deuterium. And that to them was a holy shit discovery. Can you be a planetary scientist from the 1970s? Can you tell me what that means? What does it mean, that 100-fold increase in deuterium?
Water did exist on Venus?
That's right, because remember that the cosmic abundance of deuterium is in my cup of iced tea. All of this water here, if I could count through molecule by molecule, probably 1 out of every 6,000 H2Os would not be H2O, but would instead be HDO. So 1 out of every 6,000 water molecules would be a deuterium stuck to it. Because Venus lacks a global magnetic field, when those solar ions come pummeling down on Venus's atmosphere, poof, they bust this water molecule to smithereens. And then, forget about the OH ions, then you end up with free hydrogens and free deuteriums. What's going to happen next, class?
Hydrogen escapes.
That's right. The deuterium remains. Based on what we talked about with planetismals and seed theories, is Venus massive enough to capture hydrogen from the Proto-Solar Nebula? Yes or no? Could Venus capture hydrogen from the Proto-Solar Nebula?
No.
No, it's not massive enough. It's not Jupiter. That means, Jake, there's only one place deuterium could be coming from, isn't there? Water. The increase in deuterium relative to hydrogen suggests an ocean's worth of water got, let's say, busted up by solar wind ions. And that means Venus potentially could have outgassed as much water as Earth had it protected it with a magnetic field and slightly cooler temperatures. That suggests, by the way, like fucking English here. Okay. Cool. That knocks out 65, and we're done. Ava, that is a great question. I have a lab called the rotations of Jupiter. Did I not post that yet, Ava? Because I may have not done that yet. I need to post the lab called the rotations of Jupiter. Do I have that? Wow. So assignment, let me see if I have the form here, because Ava, if you like to print it out in advance, let's do that. What lab will that be again? Shoot. You guys can't see what I'm doing. That's lab, it'll be lab 11. Hold on.
Lab 11, you said, for the next lab?
Yeah, I think assignment. Lab 11, rotation of Jupiter. Sorry, I knew I had forgotten to do some things. And I think I can, I'm just going to leave this blank, but I'm going to do browse local files. And I think I have the lab ready to go. If not, I'm going to have to do it on Sunday. Do you see? Ah, nuts. Oh, here we go. Massive Jupiter lab. So there we go. I'm not going to put a due date. I am going to put 10 points, and I will allow multiple submissions for screw ups. And there we go. Submit. So now we should see that there. I hate Blackboard. There it is. Does that help you, Ava? Where are you, buddy? Okay. We might do the hybrid 9 and 10 homework next week. I don't know. I may, instead of next Wednesday will be our last lecture. Instead of doing a problem set, would you guys rather do Well, okay. We have to decide, I have to decide whether I'm going to make you guys do the exam or give you the option to double your midterm grade. That's an outstanding question that we discussed today. So I'll figure that out next week. If we're going to do an exam, I could do practice problems for the exam. If not, we could do a problem set or something. Or I could let you guys ask me wacky questions about space. Who knows? Okay. Does that cover us for today, everyone?
Yeah.
Please do not forget to upload these assignments. Sometimes you guys forget to picture and upload it. Just do it now so you don't forget, okay?
Can I see what the last 3 words are real quick?
Oh, yeah, Greg, sorry.
Thanks.
Professor,
Yeah.
my handwriting is really, really bad for the first few questions.
Okay.
That's okay?
I should be
Okay.
able to get a gist of it. The important thing, Andrew, is that you went on the journey with us. You took the journey and you wrote stuff down. If it's not, what was happening? Did you hurt your hand or something, or?
I was using cold water for 2 hours to wash dishes, and as soon as I started writing, I realized my hands didn't work.
Oh my gosh. Is there heat out in the RV?
No, not right now. So.
Oh gosh. Okay, buddy, well, you better get that. Yes, take care, Ava. Wonderful sort of texting you. Andrew, get that fixed because the winter is coming, as they say in Game of Thrones, right? Was it propane? Is that how you heat your RV?
I have a generator and I use 2 electric heaters, and then I also have a propane heater. But I fell asleep the other day and the propane pilot light went out, and I woke up and the whole living room was filled with propane gas. So
Oh my God, buddy. Holy
I'm glad I woke up. Yeah.
Yeah,
So-
good thing you didn't light a smoke or something. Your whole life could have exploded right there.
It was
Holy,
bad, but
even a
So I
static
don't trust it.
discharge rubbing your feet on the carpet could potentially ignite if the concentration is high enough.
high enough to wake me up, thankfully.
Oh my God, Andrew, be careful.
Is there a propane detector or whatever that you can get?
That's a great idea. I learned that my smoke detector and the carbon monoxide thing don't work for that. So yeah, I'm going to look into that.
Dude.
But,
All right, dude, we're going to see about getting you a tank of propane. All right. What's a tank of propane cost?
I have 2 tanks of I have plenty of propane. I can keep getting propane. It's
Oh.
like, I think it's like, for a 30-pound tank, it's like $25 to refill it. So
Okay,
it's not
so-
bad.
So refill it and get some hot water. So you, okay, buddy, you're going to freeze in your sleep or you're going to explode in your sleep. I don't know which is going to happen.
Well, either way, I'm not going to die of COVID because I'm locking myself in my camper. So.
Okay. All right. Well, that's good. That's something good. Yeah. Stay safe, everyone. Okay, guys, I'll talk to you next Monday. Okay. Have a great weekend. Get your work done. Don't fail your classes. Okay. Bye-bye.